Hi all. So welcome to another lecture of our subject EC469 Opto-Electronic Devices. Today we are continuing with module number 1 and we'll be looking at the power generated during recombination and some of the effects that controls the semiconductor activity. So in the last lecture we have mentioned that the quantum efficiency eta is equal to the radiative recombination rate divided by the total recombination rate, or we can write eta R total is equal to the radiative recombination rate. Now let's assume that the semiconductor is connected to some kind of a voltage source and it is generating a current small I. Now the current I can write it as the rate of change of charges. So I can write basically dq by dt, or in more simpler way for the sake of explanation I can write it as total charge by the total time. Okay, so we know the electronic charge E is equal to 1.6 into 10 raised to minus 12 coulomb. So if there are n electrons being supplied, implies I can write it as I is equal to Ne by small t, where t is the total time, right? So if I want to find out the total number of electrons, then I just need to, so I can say the total number of electrons is equal to the total charge divided by the charge of an electron, which is E. So this E is basically the charge of an electron. So this is Ne by E, that is n. So this gives me the total number of electrons. So when the semiconductor is connected to a source, the electrons will be moving freely, which will finally conduct the current. So these electrons are the ones which are the charge carriers, and these charge carriers will be combining with holes and also generating new electrons to conduct the current. So the recombination rate I can say as R total is equal to the total number of electrons divided by total time, which is basically, I can say it as total number of electrons. We have already said it is n and total time is t. So I can write this as, we already know that the total number of electrons is related to the current I. So I can write the total current divided by E, because the total current is NE by T. So if you want to prove this, this is basically the total current is equal to the total number of electrons divided by T. Okay, when you divide, so R total is equal to NE by T divided by the total charge E, that is this. So this is the total current, which is this, and this is the total charge. So which will give you basically N by T, that is the recombination rate. Okay, so I can write R total as the current I divided by E, which is basically this expression, right? But for radiative recombination, the recombination rate is the efficiency, quantum efficiency, multiplied by I divided by E, because our radiative efficiency, radiative recombination rate is equal to efficiency into R total. We found that R total is I into E, so we can write RR is equal to eta into I. Okay. Now, this radiative recombination rate will also give the number of photons generated per second, because for every recombination, since this is a radiative recombination, for every recombination there is a photon generated, and the recombination rate is number of recombinations happening per unit time. So that is the number of photons generated per unit time. Okay, and each photon carries an energy h nu. Okay, so the total power, I can write as P is equal to the number of photons generated, which is RR, multiplied by h nu, because RR is units per second. So, and when you divide the energy per second, it is basically the power. So I can substitute the values for RR. This is eta into I h nu by E. This I can write as eta h into I into C by lambda E, because nu is the frequency, which is equal to C by lambda. So the power generated for a radiative recombination is given by eta, which is the radiative efficiency or quantum efficiency, radiative recombination efficiency, multiplied by h, which is the Planck's constant, I with the current which is supplied, C with the velocity of light, divided by lambda, the wavelength of light, and E, the electronic charge. So this is the power which is generated. Okay. So this is just a continuation of our previous class. Now let's look at some of the effects. The first effect is Franz-Keldysh effect. So this is given for given the name, the effect is given for the German scientist Franz and the Russian scientist Keldish. So they combined, the effect was introduced by these two scientists. So what is this Franz-Keldysh effect? So Franz-Keldysh effect gives a change in absorption in a semiconductor in the presence of a strong electric field. Okay, so you can define the Franz-Keldysh effect as the change in absorption in a semiconductor in the presence of a strong electric field. Is the Franz-Keldysh effect, which results in the absorption of photons with energies less than the band gap of semiconductor. This is a big statement, but let's analyze it a bit further so that we understand what this means. So for sake of simplicity, I am drawing the energy band diagram straight way. So usually our energy band diagram has a valence band and a conduction band. So this is the valence band, this is the conduction band. So there are energy states available both in valence band and conduction band. So there are multiple energy states available here. Similarly, in the valence band also you can have multiple energy states. And this is the band gap Eg with the energy difference Eg. This is the band gap, and there are no energy states in the band gap. Now, if there is an electron in the valence band, what happens if I irradiate with a photon of energy h nu, but the value of h nu is less than Eg? So usually the electron can absorb the energy, it can move to higher energy level, so it will absorb the energy. Now when it comes to this energy level, which is less than Eg, now there are no energy states available for the electron to occupy. Okay, so because energy states are either in conduction band or in valence band, there are no energy states in the band gap. So it cannot occupy any of the energy states, so it will maintain its position at the valence band. So that is the scenario that we have looked upon. So if I draw the absorption spectrum, okay, absorption spectrum means if I draw on the x-axis the energy in electron volt, and in the y-axis I put the wavelength. So up to Eg, up to the energy Eg, there will not be any absorption. It will be zero absorption. after the energy increases beyond Eg, so this is Eg, as the energy increases, as you supply more and more photons with energy higher than Eg, it starts absorbing photons and it will move to the conduction band. So these are the green line is the wavelength which usually absorbed by electron to go to the conduction band. This is our normal scenario. Okay. Now when you apply a electric field to this semiconductor, okay, so this is when the semiconductor is as it is. Now let's apply an electric field to this semiconductor. Some potential is applied. Now, when you apply an electric field to semiconductor, the band, both the conduction band and the valence band will tilt, because if you consider, so this is, let's say x equal to 0, this is the portion, and this is, let's say x equal to L. So this is the total length of the semiconductor is L. Okay. So when you plot, usually the y-axis is E, the energy, and the x-axis is the length x. So when you apply this electric field, you see that in this portion where you have connected positive, this has higher energy, and the energy reduces as you travel to x equal to L. So this portion has lower energy, and let's assume that this variation from higher to lower is linear. So what happens to our energy band is it gets tilted. Okay, so this will be our new energy band diagram, where you see this is EC, this is EV, this is the valence band, and this is the conduction band. It will get tilted. So if you assume a point, if you look at the previous band diagram, let's say there is a point A here and there is a point B here. Okay. Now these 2 points will be maintained as it is in the new band diagram. The band gap will still be Eg. There won't be any difference in that. Okay. But only thing is it gets tilted. Now, if I consider a electron here, okay, then it needs the Eg energy to move to the conduction band. Sorry, this is C and Ev. So it needs Eg energy to move to the conduction band. Okay. Before doing that, so this is for some voltage V. So this is for some potential that you have given, or some electric field that you have given. Let's say the potential that you have given, V is equal to V1. Now let's assume you increase the potential. So the left hand side will become more and more high energy, right hand side will become lesser and lesser energy when compared to left hand side. So it will get tilted more. So the tilting will increase, something like this, where you have applied a new potential V equal to V2 and V1 is less than V2 or much less than V2. Now if I consider the points A, if I consider A here, B will be somewhere here. You see that the point is not changing, only the band is tilting. So if you look at these 2 points, so there is an energy state available here. There is also and energy states available here, and both the energy states are actually the same energy state. That is, in conduction band and in valence band, you have the energy states in the same level. While in this case, you see the energy states are not in same level. The electron needs to attain some energy to move to the conduction band. Here also, although it is tilted, the electron needs some energy to move to the conduction band. But when the tilt is higher, when you increase the potential, you see that although the points is not changing, only because it is tilted very highly, the energy state in conduction band and in valence band are in the same line, or they are the same energy state. So what the electron does, it will tunnel to the conduction band without it need not absorb any energy. You can just tunnel to the conduction band and it will conduct electricity. Okay, so this is called as tunneling. Okay, now in this scenario, if you look at this scenario, let's give an photon. So let me draw it again. There is not too much of a tilt. There is a position A here. There is this position, let's say B here. Okay. Now let us incident this semiconductor which has been given some kind of a voltage with a photon of energy h nu 0. It is less than Eg. Okay, so Eg is not changing in any of the diagram. Eg is same everywhere. So what it does is, so what happens is the electron in the valence band sitting at A will absorb the energy and moves to some state here. Now this is, and you understand that this is a band gap and it doesn't have energy state, and the electron doesn't have enough energy to move to conduction band because the value of the photon incident is less than Eg. So the electron will stay in the, or it will acquire energy and move to some position depending on the energy it has acquired. If you look at this scenario, you see that at this position there is an energy state available at B. At B there is an energy state available for the electron to go to conduction band. Although the electron doesn't have enough energy to cross the valence band, it has an energy state available because of the tilting of the axis or the conduction band and the valence band. It has an energy state available in the conduction band. So what the electron does is, it will tunnel through and go to the conduction band. That means without having with a photon of energy less than the band gap, in an strong electric field, the electron will move to conduction band by tunneling, and this is called as photon assisted tunneling. Okay, so this is called as photon assisted tunneling, and this effect is called as Franz-Keldysh effect. So let's look at the definition once again. It says the change in absorption in a semiconductor in the presence of a strong electric field. So previously there was no electric field, so the absorption was the normal absorption. If you get an energy more than the band gap energy, you will go to the conduction band. If you get energy less than band gap energy, you will not go to the conduction band. But when you have the strong electric field, the band will tilt and absorption will happen. Okay, is the Franz-Keldysh effect, which results in the absorption of photons with energies less than the band gap of semiconductor. So the absorption is happening in a energy provider system, external energy is provided, and absorption is happening, and the semiconductor is absorbing a photon of energy less than the band gap energy, and the electron tunnels through to the conduction band. So that's what the Franz-Keldysh effect gives. Now we have seen the spectrum in the normal absorption. When you come to the Franz-Keldysh effect spectrum, this is energy, or this is the absorption spectra. Usually till Eg there won't be any absorption, and without any external electric field it was like this. Now since by applying an electric field, the absorption will start at an energy less than Eg, and it comes like this. Okay, so the green one is without applying electric field or potential, and the pink one is by applying potential. So you see that at some energy less than Eg, the photons are absorbed. Photon with energy less than Eg is absorbed and it moves to the conduction band, and this is called as Franz-Keldysh effect. So along with it, you can do one homework where you want to find the expression for electric field dependent absorption coefficient. You don't want to derive this, you can just find the expression and describe the terms used in the equation. So you can do as a homework to find just find the expression for the electric field dependent absorption coefficient. Okay, fine. So this is the Franz-Keldysh effect. The next effect is called as Stark effect. This is a basic effect which is very popular in quantum mechanics. So Stark effect is basically the splitting of energy levels in the presence of an electric field. So we say that we know that the energy levels in a semiconductor or in an atom is discrete. It can have only some particular values of energy levels. Now so let's say this is an energy level. Now when this semiconductor is connected to an electric field, what happens is it will get split into multiple energy levels. Okay, so you can assume that the semiconductor or the atom is going near to another atom. So both atoms will have energy level at the same location, say might have the same energy level, but once it is made to come near, the energy level will get split, and both atoms will have a different energy levels. This is called as a Stark effect. And the Stark effect can be linear Stark effect or quadrature Stark effect. So you can look at what is linear Stark effect and quadrature Stark effect. Okay, fine. Okay, I think we'll stop it here. And so in this class we had looked at the power generated, and we found the expression for power generated in terms of the Planck's constant, internal efficiency, wavelength, light velocity and electronic charge. And we also looked at the Franz-Keldysh effect. We defined what is that effect. We also saw what are the how an energy band diagram will change according to the applied potential and how the tunneling is happening. And we saw also the absorption spectra. So we have a homework to do, and we also saw the Stark effect and basically the splitting of energy levels. There is one more effect which is called as quantum confined Stark effect. So this is basically an extension of Stark effect which needs a bit of insight into something called as quantum wells, that we will see in the next class. Thank you.